Yes. So normally you should also press this link. So, yes. Okay. And now I should be able to log in as administrator. Yeah. You see, normally, as administrator, I also see a message when you create or when somebody creates an account. So, not created when it is confirmed. So when once you press this confirmation link in the email, then I will see this message that the SBC account successfully confirmed. Yeah, yeah. So you're making an account for him. Yeah, yeah, yeah. Yes, go ahead. this list of launch orders. It goes to whom? For Cuthbert. It's for you. It's,
What is your password? When they ask for password for credit cards,
this is the SDC.
save it.
Now you can try to log in with these accounts to make sure this works. You can also create subscriptions manually as administrator. So you can log out from this user portal. Okay.
Isn't it green?
Yes. Absolutely. You drank all the coffee.
Okay.
But maybe they can feel it.
Yeah, later on. Maybe they'll just take tea. Tea instead.
So you can then create some and groups.
subscriptions manually here now. If you go to service data and subscriptions, you can, for example, for him, he cannot create for himself. Somehow it doesn't. Yeah, okay. So you see this, all these are pending. You see the status of the subscription is yellow, it's pending. But
Sorry, go and integrate.
yes, you can come and activate all those that are pending. So go down. Yes. You see the subscription period is updated. So this information is updated based on article parameters. So maybe this to go first. This is for 1 month. So you can just press save and close and activate the other one. So those that are pending are on the top.
Automatically.
Yes, should be.
Ivan.
Mhm. Yeah.
Les mots, c'est mal. Vraiment, congratulations, je ne pense pas.
Ouais. That's a hope direct.
Mas já, quando eu sei que já uso o chão, já calma dele, só não vou dizer. É. Não, calma. Não sei nem do. But trust me, you know, what for step money.
Because we get one night salary. And the next time, like the lunch in the one. No, of the hill, like when I was coming.
Wow.
Don't miss it. Then I can feel the
Okay.
Thank you so much.
Yeah, you should go and ask because also Cuthbert he wanted to have coffee.
You also wanted to have coffee.
No, but Cuthbert, so maybe they can just refill it. I can. Yes. Thank you. Cuthbert. Coffee.
Patience coming.
But patience is coming. Yeah. Yeah, you should take coffee because now we are going to talk about coordinates and this is gonna make you sleep. Yeah, I insisted that they bring coffee because for non-surveys this is the most difficult presentation. Yeah. But because I always need to show this one because this is directly linked to our computation which we did for you. So in order to understand the report which we delivered already, I gave it to Isaacson. Then you need to understand a bit of what actually is behind it. So I really recommend you take a coffee. Yeah, you can manage the presentation easily with some extra dose of caffeine, in your blood. The coffee is here, if you want. Ah, no. Ah, she took it away. There was a dose of coffee here. Yeah.
When it comes to mathematics, but yeah, do like it.
Can I buy that? But you know how sad?
It doesn't know.
Coming up with the rotation.
You know about it?
Yeah.
Ah, good. So maybe it will not be so new at the end for you. But we will see.
No, I'm talking about
Yeah, but geodesy is basically just applied mathematics.
Yeah.
There is nothing. This is actually very simple, I would say. Normally, it's not so complex.
Sena kutabere mwana.
Aiwa, ndambotaura. Inenge ichiisirwa munhu waanenge
Udah. Guru Shanda. Bukan arti ubah.
Uno ese. Es uno con gozo. Bueno, pues sí. ¿Eh? Ah, pues sí, pero ya está, no.
So let's try to talk about coordinate systems. Shall we wait for Zuka, maybe?
Hello?
The music is for tomorrow, for the ceremony. They're testing the speakers, huh? So it has to be perfect, of course. The president will be watching, so it has to be perfect. There will be a party afterwards, or what's like open air party, or just the ceremony? Okay, so it's not with the president. They will dance with the president. No. For business. It's president. All right. So let's try to talk about this coordinate systems used in GNSS. So this doesn't work. Now it's working. So when we talk about GNSS positioning, so more or less, and coordinate systems, we are talking about something which is called the principle of trilateration. So trilateration is a method when the coordinates are computed based on measured distances. So this is something that we already talked about. Basically, what the receiver does, it is trying to measure the distance that the signal basically passes from the satellite to the antenna of the receiver. So normally, the system can measure these distances, and if you have at least 4 satellites, then you can compute the position of the point in a specific coordinate system. And now we are going to talk about these coordinate systems which are used basically in GNSS positioning. The problem here is that this whole system is very dynamic because, first of all, the satellite, they revolve around the Earth quite quickly. So I think the speed of the satellite is about 4 kilometers per second. So in order to compute positions for such a quickly moving object in space, it's not so easy. And then you have basically Earth-related dynamics, which means that the Earth rotation, first of all, then the rotation of the Earth. It basically Earth rotates around the point which we call a pole. But the problem is that the pole is not static, so the pole also moves slightly. You know, so the motion of the pole, and then on top of that, you know, the Earth is divided into several tectonic plates, and these tectonic plates, they also move. So basically everything is in motion. So in order, well, taking into all this into consideration, it's quite difficult actually to define a system, coordinate system, which basically could be used to express positions of points or objects, basically in such a highly dynamic system. And since everything is in motion, first important information about coordinate systems related to GNSS is that they have to be fixed to always to a time epoch. So whenever you do some kind of measurement, because of this, you always need to also consider a time when you perform the measurement or when you made some observation with your GNSS receiver. So, and that time, when the time period when you made this observation on the measurement in the field is called an epoch of observation. So epoch of observation means basically a timestamp, which means a date, the time when the measurement was basically performed, and this is always linked to your coordinates, which are computed by the GNSS solution. So in order to take all into consideration all these dynamic aspects of GNSS, so it is necessary to basically include them somehow into how the coordinate systems are defined in order to get this kind of precise positioning. And so far, or basically 3 different coordinate systems have been adopted in relation to GNSS positioning. So these are called so-called conventional celestial reference systems. So these are used for basically defining positions of objects in space. So this is related to the satellites of GNSS. And then we have coordinate systems related to objects on the Earth itself. So these are called conventional terrestrial reference systems. So we have celestial and terrestrial. So this is the main difference. Celestial means objects in space, terrestrial objects on the ground. And then we have these coordinate systems related to the pole motion. It's called celestial ephemeris pole. So once again, when we take into consideration the rotation of the Earth, we need to also take consideration of the position of the pole. So these 3 systems have been defined to somehow make it all work. Now, basically for our or for your system, only these terrestrial reference systems will be of main interest, as I'll explain later, but just to understand that all this is basically taken somehow into consideration or taken into account when we talk about GNSS positioning, the coordinate systems, GNSS positioning. Then the second very important information is that we have 2 different concepts. First are so-called reference systems, and the second one is so-called reference frames. So the reference system, it's theoretical definition, it's mathematics. So if you say that the beginning of the coordinate system is at the center of the Earth, this is theory, because you don't know where the center of the Earth is. You can just try to somehow estimate it or to measure it or to do something about it, but you will never know exactly where the beginning is. So this reference system, when you see somewhere written that it is a reference system, then it means it is just a theory, just a theoretical definition, including some kind of model standards for its implementation. And then we have something called a reference frame. So reference frame is typically the realization. So when you are trying to define this reference system as close as possible based on some kind of observations or based on some kind of measurements in the field. So this is what we call a frame. So it's kind of the practical implementation. So through sets of observations or measurements. And typically the reference frames can be defined for both of these systems that we talked about before. So for the celestial reference systems and the terrestrial reference systems. And the realizations are called celestial reference frames and terrestrial reference frames. So obviously, there have been several realizations. So over the history of time, when the GNSS was basically, when it was first time used for some kind of practical measurements, there have been several realizations of these reference systems. So we have several reference frames, and but we have only one reference system as a definition. So it is like you have a theoretical value for this table that it is, I don't know, 5 meters, and you can measure it 10 times. So this individual measurement, this is kind of a realization of this theoretical value, and each time you will get slightly different value. So this is the difference between these reference systems and reference frames. So now this International Celestial Reference System. So initially it was proposed by this International Earth Rotation Reference System Service, so IERS. This is an organization who is actually until today who is in charge of basically releasing the new realizations of this theoretical system. And it was formally accepted in 1997. So we are talking about things that have been basically present for quite many years now. And as I said, the realization of ICRS is called International Celestial Reference Frame, or ICRF. So this, once again, is used for positioning the objects in the space. And then we have this ITRS, International Terrestrial Reference System. Once again, it is defined by IERS, this International Earth Rotation Service. And as I said, the realizations of these theoretical systems are called International Terrestrial Reference Frames, or ITRF. The last realization is called ITRF 2014. And very soon we'll have a new one called ITRF 2020. But so far, this one is still the last one, the last realization of this theoretical system. And this is the system or the realization which currently is used by your stations. And it is also the realization that will be applied for the ZINXA CORS network. So your coordinates will be or are computed already in this realization ITRF 2014. So now let's see a bit about this International Earth Rotation and Reference System Service. So this organization, they are very important because they are in charge of defining standards, first of all, for basically the reference systems, but they're also in charge of these realizations. So first time it was established in 1987 by the International Astronomical Union and by the International Union of Geodesy and Geophysics. So these are all kinds of different organizations, not so important. And they began their operations in 1988. And so original name was International Earth Rotation Service. Then that name was changed to this International Earth Rotation and Reference System Service. So they added this reference system service because before I would say the definitions of these reference systems were not some kind of uniquely defined, but from 2003, they are in charge. So if you have some problems with the realization, then you can complain. So No, it's not really the case, but as I said, the primary objective of this International Earth Rotation service is basically to serve the astronomical, geodetical, and geophysical community. So this is some kind of, I would say, non-commercial organization. They just do things and then basically they provide some kind of services, which is quite nice of them. So what they do, they provide this ICRS, the definition and also the realization. So typically you will see later, you can go to the website, you can download, for example, the realization of this celestial system. They also provide this theoretical definition for ITRS and also the realization, so ITRF. Once again, you can go to the website and you can download coordinates or even data for a special network that is called IGS network. I'll tell you about them later. So all free of charge, which is nice. So for example, we also, when we computed your network, we also use the data. We also use the ITRF coordinates of IGS stations. So I'll come to that. And obviously, it is also necessary to be able to go from this celestial system to the terrestrial system, because you, as an end user or an end beneficiary of this technology, you are using both the satellites and you're also using the ground stations. So you need to combine these two coordinate system, and these parameters, once again, are defined by IERS. Obviously, since the system is very dynamic, so these dynamic changes in the coordinate systems, there are once again, these variations are in the Earth orientation parameters. So this is once again done by them. And once again, you can go to their website and download everything for free. So, and in addition, they also provide some standards, some models, all related to basically coordinate systems in GNSS technology. So from this point of view, they are a very important organization, and we are using a lot of information from them. So as we said, one of the main tasks of this International Earth Rotation Service is to define this International Celestial Reference System. And basically, what does it look like? This celestial reference system, so the system which we use for basically providing coordinates of spatial objects, is sometimes called Earth-centered inertial system, or ECI. And as I said, it's mainly used for description of satellite motion. In fact, are you using this system when, for example, I have seen this ZIMSAT-1? Are you working in this system or not? This coordinate system, or have you heard about this system before? This celestial reference system? So never, or no? Okay. Anyhow, so because the GNSS satellites, GPS, GLONASS, Galileo, they are primarily expressed in this coordinate system. So how is it defined? The theoretical definition: origin is the Earth center of mass, or geocenter. So once again, this is a theoretical value. And the fundamental plane is the mean equator of the epoch J2000.0. The principal x-axis is pointing to the mean vernal equinox. So this is some kind of spatial direction which is defined by some extraterrestrial object. And the z-axis is defined by the direction of the Earth mean rotation pole at these two J2000. So if you have a look at it from different perspectives, so this is what it looks like. So if this is the Earth, then this celestial reference system is a Cartesian geocentric system, XYZ, right-hand oriented. And so this is some kind of spatial orientation. It's called the vernal equinox direction. This is the plus x axis. Plus z is this mean pole position for the epoch J2000.0. And the y-axis, it just complements this Cartesian system. So this is the theory. This is what it is defined by theoretical definition. And now, as we said, the practical realization of these coordinate systems are called frames or reference frames. And there have been several reference frame for this celestial reference system. So ICRF1, ICRF extension 1, ICRF extension 2, ICRF2 from August 2009. So how it is defined, as we said, this is the reference frames are always defined by some set of points with coordinates, and the realization of the celestial reference systems are the positions of stars. So we have different techniques that basically can receive basically electromagnetic waves from this so-called extra terrestrial objects. So some kind of radiation which can be basically monitored and measured. And this reference frame from August 2009, it contains precise positions of 3,414 radio astronomical sources, some kind of stars. And what it looks like, basically you have this name of the realization, you have the destination, so these are the names of the stars, and then the right ascension and declination, these are basically the positions of stars in space using this coordinate system. Now, why is this important? As it's part of kind of, as they say, the GNSS is kind of interdisciplinary, I'd say, subject. So you need to know a bit about everything, but not so much into detail. So I'm not an astronomer, so, but this information are actually used when we try to actually express positions of GNSS satellites in space, taking into consideration that the velocity is about 4 kilometers per second. So obviously you cannot measure, you cannot, the satellite is not able to send its position every second because it is simply not possible. So what we use in this case for computation of satellite positions are so-called Keplerian elements. So if you have a celestial body, so this is the satellite, then we have this plane of reference, which is this plane of reference for the ICRF. And then we have the reference direction. This is this vernal equinox, or this plus X, if you prefer. And then the satellite is described by this element called ascending node. This is when the satellite, this is the orbit of the satellite. And basically ascending node, this is the intersection of the orbit and the reference plane. Then we have the inclination. So for GPS, this is this 55 degrees, for example. Then we have argument of periapsis. Then we have the true anomaly. And then we have this longitude of ascending node and argument of periapsis. So these are the parameters which actually the satellites transmit as part of the navigation message. And these parameters are in this ICRF realization, which means that what the GNSS receiver does, it basically accepts this, so it will receive these parameters as part of the so-called broadcast ephemeris, and these are then used for the computation by the receiver, computation of the position of the satellite. So obviously, the satellite or the receiver needs to also know some kind of variations of these components, otherwise the computation of position of the satellite would not be accurate enough. So, and this approach is used for the GPS, Galileo, and Beidou. So, as I said, except for these Keplerian elements, there are some kind of periodic terms, basically to account for the solar radiation, gravity perturbations, etc., etc. So, some kind of correction parameters, which are then used by the receiver, and then the receiver can use this information for positioning, I would say. What is important that, as I said, there are some prediction parameters, which is part of the navigation message. And as a conclusion of all this, the accuracy of computation of position of satellites is about 1 meter. So this is something which is called so-called broadcast ephemeris. So this information, these Keplerian elements, are stored in the so-called navigation are transmitted as part of the navigation message, but can be stored and displayed in this RINEX navigation files that we already saw before. So this is the RINEX, and all these basically parameters. This is for satellite GPS satellite 1 in this case. These are the Keplerian elements plus the correction parameters, which are used for the computation of positions of satellites. So this is where the celestial reference systems and celestial reference frames are used in GNSS positioning. We have also something called precise ephemeris. So precise ephemeris can be computed in post-processing, I would say. So they are not directly transmitted by satellites, but they are computed a posteriori after basically observation of the satellite. And for example, these are computed by different organizations. They are also published, and in this case, several other information or several other aspects are taken into considerations, such as the clock records or the clock corrections, then the satellite velocity,